Welcome to lesson 2.9 on two variable inequalities. My name is Mr. Teal, and I'll be taking you through this lesson today. So you might remember we've been talking about inequalities throughout this unit. So an inequality is something like x is less than 5, x is greater than or equal to 3, and so on. So we have the basics of inequalities down already. Now today we're going to introduce the concept of two variable inequalities. So instead of just having x or y or one variable, we are now going to introduce two variable inequalities. So you might see something like y is less than 3x plus 4. Y is greater than or equal to 5x minus 9. So you're going to be seeing lots of equations almost that look like slope-intercept equations, but the only difference is we are going to be looking at inequalities. So let's go ahead and talk about our first bullet point here. So an inequality in two variables whose graph is a region of the coordinate plane that is bounded by a line is defined as a linear inequality. So again, these linear inequalities are going to follow very closely with our knowledge of slope-intercept form, and we are going to be able to convert some of these inequalities into slope-intercept form, which helps us graph them and learn some more about them. So next up, we have the boundary is a line in the coordinate plane that separates the solutions of the inequality from the non-solutions. Points of the line itself may or may not be solutions. So if you were talking about a regular inequality that we remember, so for example, if you had something like x is less than a number or x is greater than or equal to a number, this inequality is going to tell us whether or not the number itself is going to be included in the solution set. And this is very similar to the way we're going to do this for linear inequalities as well. So if we're looking at x is less than a number, for example, this inequality does not have a line underneath it. So it means that we are not including this number inside of the inequality. So I'm going to say the number is not included. Okay? Now, on the other hand, if we look at x is greater than or equal to a number, this little line underneath the inequality tells us that we are including this number. And so I'm going to say this number is included. All right, so always remember, if we have less than or greater than with no line underneath, that means the number is not included. If we have less than or equal to or greater than and equal to, that means the number is included. Okay, so we're going to notice that in our lesson today, we are kind of tying that idea in as well. Next up, we have the set of points P in a coordinate plane that are on one side of the boundary of the graph of an linear inequality is called a half plane. So the portion of the graph that is above or below the boundary line is going to be called the half plane. Last but not least, a test point is a point that you pick on one side of the boundary of the graph of a linear inequality. If the test point makes the inequality true, then all of the points on that side of the boundary are solutions to the inequality. If the test point is false, so if it makes the inequality false, then all points on the other side are solutions, okay? Now, my recommendation to you, this might not make sense right now, but it's gonna make sense in a little bit. My recommendation to you is always use 0, 0 as your test point, unless it's on the boundary. And you'll see what that means a little bit later on. But when we are testing points, you always want to test easy points. So the easiest point that we have is 0, 0. So that's the point I want you to always test unless it is on the boundary. If it is on the boundary line, then you're just going to have to find another point that is a very easy point to plug in to your inequality to see if it's true. So let's go ahead and take a look at a couple of visual representations of our vocabulary. So if you look at the graph on the left-hand side, this is a dotted line, right? It's dashed. So dashed lines are going to tell us a little bit something about our inequality. So our graph is already given to us, but I want you to write down a couple of characteristics of this graph. So first of all, we see that this line is dashed. Now, a dashed line is going to tell you that we're dealing with either a less than or a greater than linear inequality, okay? So if you have a dashed line, you know that you're going to have a less than or a greater than sign, okay? Now, moving on to some of the more specific vocabulary words. So if we look above this line or below this line, this is going to be referred to as the half plane. This portion on the bottom section of the boundary is also referred to as the half plane. So if we are above the line or below the line, we are talking about the half plane. Now, the line itself, again, is referred to as a boundary. Okay, because that is going to represent our inequality right there. That is called the boundary. Now, also, this side, the solid line, is also a boundary for a different inequality. Okay, so that's just a visual representation of some of our vocab words. Now, if we look at the right-hand side, this graph is a solid line. And so what a solid line tells us is that our inequality is going to be a less than or equal to, or a greater than and equal to. Okay, so if you have the line underneath the inequality, that means the boundary on your graph is going to be a solid line. If you have just the inequality themselves, so less than or greater than, that means that your graph is going to have a dashed line as a boundary. Okay, so just a couple ways to tie in the vocab words. You could also say on this graph that this portion down here is the half plane. Also, the portion above the boundary is the half plane as well. All right, so let's talk about how we actually are going to graph and represent the solutions of linear inequalities. So when and how to shade half planes. So the way that we show the solutions of an inequality when we're looking at linear inequalities is we graph the solution and then we shade it, okay? So I want you to pay very close attention to how we're gonna do this. So let's look at example number 1. We have y is greater than x minus 2. As you can see, the boundary is already drawn for us. So the first thing we're always gonna do is draw the boundary. In this case, it's already done for us. And the second thing we wanna do is we wanna determine if our line is gonna be dashed or solid. So in this case, as you can see, we just have the inequality. We don't have a line underneath it. So that means that we are going to use a dashed line. Okay, so let's go up here. I just want to write a quick note about that. So if you have less than or equal to or greater than equal to, that means you are going to use a solid line. Okay, now alternatively, if you have less than or greater than, you are going to use a dotted line or a dashed line. Okay, so always keep that in mind. If you have just the inequality, you are looking at a dashed line. If you have the inequality with the equals underneath it, you are going to be using a solid line. Okay, so let's go back to the problem. So we're using a dashed line because we just have the inequality. And also, I want you to notice that y is greater than x minus 2. This means that all of the y values that are possibilities for your inequality have to be larger than the boundary itself, because this boundary represents x minus 2. So we are going to be shading above the line, because again, that y value has to be greater than that boundary. So that means all of the possible solutions to this inequality lie above the dashed line. So I'm going to shade in the dashed line. So what I'm going to say here is that this is the solution. Any one of these ordered pairs that lie within that solution are going to work for the inequality. So let's go ahead and test one out. So if I were to test a point that is within the solution set, let's go ahead and test the point 0, 0. So if I were to plug this into that inequality, I want to double check to make sure I did it right and make sure it actually satisfies the inequality. So if I were to plug in 0, 0, I would have 0 is greater than 0 minus 2. Then I have 0 is greater than negative 2. Well, is that a correct statement? Yes, 0 is greater than negative 2. So that means, yes, that is a solution. It does satisfy the inequality. And that's going to be the same for any one of the ordered pairs that you try that's within the solution set. All of those ordered pairs are going to satisfy the inequality. Let's go ahead and look at example number 2. Y is greater than or equal to negative 2/3 x plus 1. So the first thing I always want to look at is I want to see what is my inequality. Since I have greater than or equal to, this tells me, according to my criteria up here, I'm going to have a solid line. And also, I'm looking at all of the values of y that are greater than or equal to this equation. So that means I'm going to have to shade above because all of the y values are going to be bigger than this boundary line. So I'm going to shade all of the values above the boundary. And again, since we have a solid line, this means that all of the points on the boundary are also solutions. So I'm going to say solid slash above. Cool? So again, all of these ordered pairs, no matter which one you use, are going to work in your inequality. Let's look at example number 3. Y is less than x minus 2. So first thing I'm going to do is I'm going to look at this inequality. As you can see, there's no line underneath, so this is going to be a dashed line. So my boundary is going to be dashed, as we can see from the graph. And also, I'm looking at y is less than x minus 2. So since we're looking at all the y values that are less than the boundary line, that means I am now going to shade below the boundary. So underneath that boundary, go ahead and shade in all of those values, and that is going to be your solution set. All right, last but not least, let's go ahead and look at the last example. So we are going to have y is less than or equal to negative 2/3 x plus 1. First thing I always look at is to see, well, is this going to be a solid or a dashed line? Since there is an equal sign underneath the inequality, that means I am including all of the values on the boundary. So that's going to be a solid line. And since I have y is less than or equal to, that means y, all of those values are going to have to be less than or below the line. So I am shading below my boundary line. And all of those values are going to be your solution. All right, so now that we know how to shade and when to shade, let's go ahead and move on to a more involved example. So on the next page, we're going to look at example number 1. This says graph y is greater than or equal to negative 2x plus 1. Now, the first thing we're going to do if we have to graph a linear inequality, I want you to figure out what your boundary line is going to be. Your boundary line is literally just going to be your inequality with an equal sign. So we're going to say our boundary line is y equals negative 2x plus 1. That is the line that we are going to graph on our coordinate plane using our knowledge of slope-intercept form. Now, the second thing, before you graph, I want you to figure out whether your line is going to be solid or dashed. Okay, so the first thing, we always write down the boundary line equation. Second thing is we figure out if it's solid or dashed. So we're going to take a look at our inequality. Our inequality here is greater than or equal to. So if I have greater than or equal to, this little line beneath is going to tell me I am going to use a solid line. So now I know once I graph this, I'm going to connect the dots with a solid line, and I am good to go. It's very important to determine, because if you don't put the correct type of line, you will not get the correct answer. So I'm going to go ahead and graph this line using my knowledge of slope-intercept form. I know my y-intercept is 0, 1, so I'm going to plot a point at 0, 1. Then I'm going to use my slope to fill in a couple of additional points. My slope is negative 2, so I'm going to go down 2 to the right 1, down 2 to the right 1. And let's go ahead and do 1 point above. I'm going to go up 2 to the left 1. And now I'm going to connect those dots using a solid line. And that is going to be the line that represents my boundary. Okay, so after we actually graph the line, what I want you to do is we are going to choose a test point. Like we said on the first page, we said we are always going to test 0, 0 unless it's on the boundary. Since 0, 0 is not on the boundary line, I am more than allowed to test it. So we're going to go ahead and test 0, 0. So I'm going to say 0, 0 is my test point. So if I'm testing an ordered pair, what I'm going to do is I'm going to plug in that x value and that y value into my inequality and see if it's true. So I'm going to plug this in. So I say 0 is greater than or equal to negative 2 times x is 0 plus 1. Now let's see what we get. 0 is greater than or equal to negative 2 times 0 is 0. 0 plus 1 is 1. Is 0 greater than or equal to 1? Absolutely not. So I'm going to cross this out because this is not a true statement. This is a false statement. So what that means is I am not going to shade wherever my test point is because my test point did not work. That means it is not part of the solution set. So I'm going to have to shade the opposite side of the boundary or the opposite half plane because that is going to be my solution. All right, so if your test point works, then that means you shade the part with your test point. If your test point does not work, then you shade the opposite side of your test point. So then this right-hand side is going to be my solution. And that is how you graph a linear inequality. All right, let's go ahead and look at example number 2. So example number 2, I have graph y is less than negative 2x plus 1. So like I said before, the first thing I'm going to do is I'm always going to put my boundary line equation first. So I'm literally taking this inequality and replacing it with an equal sign. So I say y is equal to negative 2x plus 1. Now the second thing I do is I ask myself, is this going to be solid or dashed? Well, if I take a look at my inequality, I can see that my inequality is a less than sign. And since I have no line underneath my less than sign, this is going to be a dashed line. So make sure when you graph this, you put a dashed line. All right, so let's go ahead and graph this using our knowledge of slope-intercept form. So I have a slope-intercept of 0, 1, so I'm going to put 0, 1 on my graph. Then I have a slope of negative 2, so I'm going to go down 2 to the right 1, down 2 to the right 1, and let's do 1 in reverse, up 2 to the left 1. And this time, I am not going to connect them with a solid line. Instead, I'm going to use a dashed line. And that is going to be my boundary line. So now I can move on. All right, so just like we did before, we're going to use a test point. Always use 0, 0 unless it is on the boundary. Since 0, 0 is not on the boundary, I'm going to test it yet again. So test point is 0, 0. So I'm going to plug 0, 0 into this equation and see, or sorry, into that inequality and see if it satisfies the inequality. So if I plug this in, this is x, this is y. I'm going to say 0 is less than negative 2 times 0 plus 1. Let's go ahead and solve that. Negative 2 times 0 is just 0. So I have 0 is less than 0 plus 1 is 1. Is 0 less than 1? It absolutely is. So that means yes, this is true. It worked. So since it's true, I'm going to shade the section of the graph that includes my test point. So this time, I'm going to shade the bottom portion of the graph. So now you can see if the test point works, you are shading that portion of the graph. All right, so this is going to be the solution to my inequality. All right, let's go ahead and move down to a word problem. So we're going to go down to example number 3. We have Tina. Tina is going to buy P pounds of pasta salad and C pounds of chicken salad for a party. The pasta salad costs $4 per pound and the chicken salad costs $6 per pound. Tina has at most $28 to spend. Write and graph an inequality that represents the relationship between P and C. All right, so let's figure out what we have here. So first thing we have, pasta salad costs $4 per pound. Second thing we have, chicken salad costs $6 per pound. Third, and probably one of the more important things we have, is that Tina has at most $28 to spend. So we cannot spend any more than $28. That means our total cost is going to have to be less than or equal to $28. All right, so we're going to go ahead and relate some things before we actually write an equation. So if I have $4 per pound of, that's pasta salad, and I'm adding that to $6 per pound of chicken, and that has to be less than or equal to $28 because I only have $28 to spend. So now I'm going to use these two variables that are given to me. P is the number of pounds of pasta salad. C is the number of pounds of chicken salad. Let's go ahead and write the equation using the variables. So I'm going to go ahead and say this is pasta, so 4P plus 6C has to be less than or equal to 28. Now you might notice this is not in slope-intercept form. So I'm going to have to put this into slope-intercept form. Now, you're thinking to yourself, there are no x's and y's. I have p's and c's. This is a little bit tricky because what we're going to have to do is we're going to have to look at our graph to the right here and see, well, what is x and what is y? Well, if you take a look here at p, p is on what normally is referred to as the y-axis. So I'm going to say p is represented on the y-axis, and c is represented on the x-axis. So what this is telling us is that p is on the y-axis, so p is really interchangeable with y here, and c is on the x-axis, so c is really interchangeable with x. So what I'm going to do, I'm always trying to get y by itself if I'm putting this in slope-intercept form. So in this case, I am going to isolate p, because again, p is represented by our y-axis, so isolate p. Okay, so we're going to have to get p by itself. So the first thing I want you to do is we are going to subtract 6c from both sides. Now, if I subtract 6c from both sides, my new inequality is going to be 4p is less than or equal to negative 6c plus 28. Then I want to get p by itself, so I'm going to have to divide both sides by 4. And whatever I do to one thing, I must do to all things in my equation. So now my inequality is going to be p is less than or equal to negative 6 over 4. That is going to be simplified to negative 3/2. So I have negative 3/2 c plus 28 divided by 4 is 7. So this right here is my linear inequality that I'm referring to. All right, so let's go ahead and draw our boundary. But first, I have to figure out what my boundary line is going to be. So my boundary line is going to be the same thing, just with an equal sign. So I'm going to say my boundary is p is equal to negative 3/2 c plus 7. All right, now let's figure out if we are solid or dashed. Since I am looking at less than or equal to, that is my inequality, that tells me that this is going to be a solid line because I am including all of the values on the boundary because I have less than or equal to. Okay, so now we're going to go ahead and graph this using the fact that we know what the line is and we also know that it is a solid line. So using my slope and my intercept, I'm going to put my intercept first on the graph. So I go to 0, 7, up 1, 2, 3, 4, 5, 6, 7. And now I'm going to use my slope to go down 3 to the right 2 a couple of times. All right, and since this is a solid line, I'm going to use my straight edge to connect those dots. And that is my inequality. Now I have to figure out where I'm shading. So there's a couple ways you can do this. First of all, you can recognize that we are looking at less than or equal to. So that means all of the shaded values need to be below the graph, or we could use a test point. So if we were to use a test point, let's say 0, 0, we're going to say testing 0, 0. And what this does is we are going to plug this in. So if we plug this into the inequality, I'm going to say 0 is less than or equal to negative 3/2 times 0 plus 7. And that gives us 0 is less than or equal to 0 plus 7, which is just 7. Since this is a true statement, we are going to include the section of the graph that has 0, 0. So I'm saying true. So I'm including 0, 0 in my solutions. So that means I'm going to shade underneath my graph. And that is going to be the solution set. Now, what this is telling you, so if we're going to put this solution into terms, because we are doing a word problem here, this means that Tina spends $28 on the line, and she spends less than beneath the line. So that's how we kind of make sense of what this graph means. So if she spends an ordered pair that is on the line, that means she is spending the $28 in full. If she is spending any of the ordered pairs that fall beneath the line, that means she is spending less than $28. And this, again, is the solution. All right, let's look at the next page. So if we go to example number 4, we are now looking at absolute value equations. So we did talk about absolute value equations in lesson 2.8. Now we're going to relate it to the inequalities. So graphing an absolute value inequality. The first thing I'm going to do if I'm graphing an absolute value inequality is I'm going to find the vertex. So the vertex is going to be opposite inside, comma, outside. So this vertex is going to be 1, comma, -3. Right? And I'm going to go ahead and put that on my graph here. 1, comma, -3. Now I'm going to figure out what my boundary is. I know that my boundary is going to be that graph, but my boundary, again, is not going to include the inequality. I'm just going to say my boundary is y equals -2 times the absolute value of x minus 1 minus 3. So we're going to go ahead and graph this. So if I'm graphing this, I'm starting at my vertex, and I'm using the fact that a is equal to -2. Okay, so that means my slope essentially is going to be -2 over 1. So I'm rising -2 and running 1 on the right-hand side of this graph. So I'm going to go down 2 to the right 1, and then down 2 to the right 1, down 2 to the right 1. Okay, and then if I'm looking on the left-hand side, I'm going to go reverse. So I'm going to go down 2 to the left 1, down 2 to the left 1, down 2 to the left 1, or I'm essentially reflecting over that axis of symmetry right there. So now we're going to determine if we have a solid line or a dotted line. So I'm going to say solid / dotted or dashed. So let's go ahead and take a look at our inequality. Since our inequality is a greater than or equal to sign, I am looking at a line here. So that means this is going to be a solid line. So my boundary, I'm going to connect those dots with solid lines because I am looking at an inequality that has the equal sign underneath. All right, cool. So that is going to be the graph. Now I'm going to figure out where I'm shading. So I'm going to do my test point. Our test point is always going to be 0, 0. So I'm testing 0, 0. So let's go ahead and plug that in. So if I plug 0, 0 into that absolute value, I'm going to have 0. And again, I'm going to include the inequality here. So 0 is greater than or equal to -2 times 0 minus 1 minus 3. The absolute value of 0 minus 1, that's going to be +1. -2 times +1 is -2. So 0 is greater than or equal to -2 minus 3. Then I'm looking at 0 is greater than or equal to -5. Is that a true statement? Yes, 0 is greater than or equal to -5. So that means, yes, this is true. And so wherever I have my test point is going to be up here. I am going to shade above that graph. So all of these values that are above that boundary are going to be part of the solution set. So all of these ordered pairs are part of the solution set. I'm going to write solution. Okay. So let's go down to example number 5. So same exact thing. The only difference here is we have 4 minus y is greater than the absolute value of x plus 2. This is not in standard form. Okay, we want to get y by itself so that we can actually graph this thing, so we can get something that looks like the parent function. So let's go ahead and move some things around. So first things first, I'm going to subtract 4 from both sides because I want to get y by itself. So I'm going to subtract 4 from both sides. Remember, the absolute value is in itself a unit. We cannot combine the -4 with the +2 because this +2 is within the absolute value, so we cannot combine terms. They are not like terms. So now we're going to have -y is greater than the absolute value of x plus 2 minus 4. Now, in order to get rid of that negative, I'm going to have to divide everything by -1. So I'm going to say divided by -1, divided by -1, divided by -1. Since we are dividing by a negative number, that means we have to flip our inequality. Okay, so don't forget to do that. So we are going to have y is less than negative absolute value x plus 2. -4 divided by -1 is +4. Okay, so this is the inequality that we are now looking at. So let's go ahead and find our vertex. Our vertex is going to be opposite inside, comma, outside. So our vertex is -2, comma, 4. Opposite inside, comma, outside. Now our boundary is going to be this inequality just with an equal sign. So I say y equals negative absolute value x plus 2 plus 4. So that's the boundary that we're looking at here. Let's go ahead and figure out if this is going to be solid or dotted. So since I have a greater than sign and there's no line underneath, I am looking at a dashed line. So now we can go through and actually graph this thing with a dashed line. So first things first, I'm going to put my vertex down, -2, comma, 4. And then I'm going to use that a value. Right here, I know that a is equal to -1 over 1. So that means I'm going to be going down 1 over 1, down 1 over 1, and so on. So let's go ahead and use this. We're going to say down 1 to the right 1, down 1 to the right 1, and so on. And then on the left-hand side, I'm going to do reverse, down 1 to the left 1, down 1 to the left 1, and so on. And again, I am including a dotted line instead of a solid line. And on this side, I have a dashed line, and so on. Okay, so now we're going to figure out where our solution is. So let's go ahead and test 0, 0. So if I test 0, 0, 0, 0 somewhere right here, it's not on the boundary, so I am allowed to test it. So I'm going to plug this in to my inequality. So I say 0 is less than negative absolute value of 0 plus 2 plus 4. I'm plugging this into that inequality. Then I have 0 is less than the absolute value of 0 plus 2 is just 2, -2 plus 4. Then I have 0 is less than 2. Is that a true statement? Why, yes, that is a true statement. So that means this is true. So I'm going to include 0, 0 inside of the solution set. All right, so this is going to be the solution of our inequality. All right, awesome. Let's move down to the next part. So example number 6, what inequality does this graph represent? So now we're going to go in reverse. We're going to look at the graphs and we're going to try to figure out what the inequalities are in response to what the graph shows. Now, as you can see, this graph right here is going to be linear. So that means we're going to have a y equals mx plus b kind of a situation. Okay, so make sure we're aware of that. Now let's write what we know about this graph. So the first thing we know is that this is a linear graph, like we said before, okay? The second thing we know is that we are going to be highlighted below. So we're gonna say shaded below, and we also know that our shading is going to be a dashed line. So I'm gonna say shaded below the dashed line. Okay, now the dashed line, let's go ahead and talk about what this means to us. So shaded below means that we're going to have y is less than something, right? Because we're shading below. And since it's a dashed line, that means we are just going to have the inequality and we are not going to have less than or equal to, okay? So we have y is less than because we have dashed, and now we have to figure out what our slope and our intercept are so we can actually put that equation in. So y equals mx plus b, let's go ahead and see what the intercept is. The intercept here is going to be 0, 1. So I have b is equal to 1. And then let me find my slope. My slope here, I see that this is a point, and I also see that this is a point. So my slope is going to be down 1 to the right 2, down 1 to the right 2. So m, my slope, is down 1 to the right 2, -1/2. So now we're going to plug that information in, and we're going to get our answer. So we have y is less than, I can't remember which pen I used, I think it was this one. Y is less than -1/2 x plus 1. And that is going to be the linear inequality that represents this graph. All right, let's look at example number 7. So first of all, let me talk about some of the things I know. I know that this is an absolute value. So we're going to have to use the absolute value formula to fill in some of the blanks. I know that my vertex is this point right here, -1, 1, 2, 3, 4. All right, that's good to know. I know that my solution is shaded above. And I also know that I'm looking at a solid line. So let's go ahead and fill in some of the blanks here. So if I am shaded above, this tells me that y is going to have to be greater than, because I'm looking at values above the graph. And since it's a solid line, I'm going to have to include equal to, okay? Solid lines tell me greater than or equal to. All right, now we're going to have to use what we know about the absolute value graph to put that into an absolute value function. So absolute value functions, we are now going to look at A. We need to figure out what A is because that's what comes first. So our A value, the value that goes in front of the absolute value, is determined by the slope. So if I'm looking at the slope of this right-hand side, I'm going down 1 to the right 1, down 1 to the right 1. So my slope essentially is -1. That's helpful because I know that now I'm going to have -1 out front of that absolute value sign. So now I have -1 times the absolute value of the vertex. So I have x. Opposite of x is going to go inside the parentheses, so +1. And then I have outside to the right, +4. So I can simplify this a little bit. I'm going to say y is greater than or equal to negative absolute value x plus 1 plus 4. And this is the inequality that represents that graph. All right, last page. Let's go to our last example for today. Example number 8, we have open-ended practice. You want to buy some CDs that cost $10 each and some DVDs that cost $15 each. You have $45 to spend. So a couple different things we have here. CDs that cost $10 each and DVDs that cost $15 each. Most important part, you have only $45 to spend. Okay, so we're going to write an inequality that represents the situation where C is the number of DVDs, or excuse me, C is the number of CDs, and D is the number of DVDs. All right, so let's go ahead and write an inequality. So if it's $10 per CD, for CDs, I'm going to put 10D. And then I'm adding that to, we have $15 for DVDs, so I'm going to put plus 15D. Oh, I messed up, my bad. This one is supposed to be a C. We're just going to remember that that one is a C and this one's a D. My bad. And then we only have $45 to spend, so I'm going to put that 10C plus 15D has to be less than or equal to $45. Okay, so now we're going to have to put this in slope-intercept form so that we can actually graph it. So what I want you to notice about this graph, D is on what normally is the y-axis, and C is normally on the x-axis. So this means instead of y, I'm going to have D. Instead of x, I'm going to have C. So I know that D should go first if we're going to follow slope-intercept form. So I'm going to go ahead and get D by itself. So what I have to do is I have to subtract 10C from both sides. Subtract 10C from both sides. And now I'm going to have 15D is less than or equal to negative 10C plus 45. Now the next thing I have to do is divide both sides by that 15D. So I'm going to take both sides and say divide by 15D, divide by 15D. I'm going to do this to all of my terms here. And now I am looking at D is less than or equal to negative 10 divided by 15. Oh, my bad. I shouldn't have been dividing the D. I am making so many mistakes right now. Oh my goodness. So we're not dividing the D out. Obviously, we're just looking at the 15. It's been a long day. Oh my goodness. Negative 10 divided by 15. I'm going to simplify that fraction. So this is going to simplify to negative 2/3 C. And then 45 divided by 15, that's going to be plus 3. Okay, so we finally made it, you guys. So we're going to graph this. And in order to graph this, I need to look at what my boundary line is going to be. My boundary is going to be that same thing with an equal sign. So I'm going to say D is equal to negative 2/3 C plus 3. So we're going to go ahead and graph this on our graph, but we also have to check and see, all right, what is this going to be? Is this going to be solid or dashed? And since I have less than or equal to, this tells me that I'm going to have a solid line, which means I'm good to go to connect the dots with the solid line. So let's go ahead and graph this. If I have negative 2/3 c plus 3, my y-intercept is going to be 3. I'm going to go ahead and increase the scale here. So I'm going to say this is 1, this is 2, and this is 3. And then same thing on the other side. This is 1, this is 2, this is 3, just because we have a lot of room to work with. So when we go up to 3 here, I'm going to put a point. And then I'm going to use my slope to go down 2 and to the right 3. So I'm going to go down 1, 2, to the right 1, 2, 3. Okay, so this is going to be my new point, and I'm going to connect those with a straight line because I am allowed to with my inequality. All right, so now I want you to take a look at this. We have less than or equal to, so that means our solution is going to have to be below the boundary. So if I'm going to put this on my graph, my solution set is below the boundary because I have less than or equal to. And of course, you can always put a test point to figure out whether or not you got it correct. So if you were to test, say 0, 0, so I'm going to say test 0, 0. All that you would do is plug that into the inequality. 0 is less than or equal to negative 2/3 times 0 plus 3. And we know that 0 is less than or equal to 3. So that means we're good to go. So we are shading right here where 0, 0 is. So that's correct. All right, so let's go through a couple of reasoning questions. So why did the graph in B only include quadrant 1? Well, the reason that we're only including quadrant 1 is because we have positive values for y and positive values for x. And as you know, you can't have negative numbers of CDs or negative numbers of money, right? You can't have negative money. Well, you can, that's called debt. But anyways, that's not applicable here. So we're gonna have, it is not reasonable to have negative items or money, right? You can't have negative items or money, so we are not going to include the other quadrants because the other quadrants have negative numbers, and it's not reasonable to have negative items or money. Now, D, can you buy 3 CDs and 2 DVDs? Well, let's go ahead and test this out. If you want to figure out if you can buy 3 CDs and 2 DVDs, all you have to do is plot 3, 2 on your graph and see if it lies within the solution set. So if we were to graph 3, 2, we would go to the right 3 and then up 2 here, and I can see that 3, 2 does not fall inside my solution set, so no, I cannot. And the reason is I don't have enough money to. And if I were to actually plug that in, so if I were to say, well, I need to have D is less than or equal to negative 2/3 C plus 3, if I were to plug this in, I would have D is really 2 here. So I have 2 is less than or equal to negative 2/3 times C, which is 3, plus 3. Well, I know that 2 is less than or equal to negative 2/3 times 3 is negative 2 plus 3. So 2 has to be less than or equal to 1, and that is not a true statement. So for that reason, since that's not true, and because it doesn't fall within the solution set, that means that 3, 2 is not an acceptable ordered pair, so I cannot buy 3 CDs and 2 DVDs because I don't have enough money. So no, I cannot, because 3 CDs and 2 DVDs surpasses my budget. Okay, so this is going to be the answer here. No, I cannot buy 3 CDs and 2 DVDs because it surpasses my budget. I do not have enough money for it. All right, guys, that was lesson 2.9 on linear inequalities. Thank you for joining, and we will see you here next time.